All right. Welcome to the Neural Information Retrieval podcast. This is 6th episode. It's Sergi Castella speaking, as usual, with our partner in crime,
Andrew Yates from the University of Amsterdam.
Professor at the University of Amsterdam. Okay, so today we have a very special paper to discuss because we're getting a little bit out of our usual comfort zone, I would say. We're going to discuss the OPT paper, which is this paper from Facebook, or well, should I say Meta? I think that their GitHub repo is still not rebranded in terms of like the Facebook research.
It is still Facebook research, yeah.
So I think that we're still in the transition period of that. Anyway, so we're going to discuss this paper. But before we get into that, quick mention. I've recently made this form so that you guys can sort of send us who you are and like some opinions you have about the podcast and what topics you'd like us to discuss. So like, please, you will find a link in the description and you can just quickly do that. It's just like a minute or two. So we really appreciate your feedback. That said, I know you, Andrew, have been very recently to the ACL conference, which was happening last week from when we were recording this. It happened in Dublin, right?
Yeah, no, it was an interesting conference.
So, would you like to share like some quick thoughts on how it went? I mean, it was like you said your first big conference in person after.
Yeah, the first in person since I think February 2020, so a little while, but it's nice to have them again. Yeah, so one theme I noticed goes back to some of the other things we're discussing, like this pre-training for dense retrieval is becoming very popular. So most of the papers that were interesting have been on archive for some time. They were nice papers. I'd read them already, but it's just a really big theme at the conference, like different pre-training approaches to get the dense retrieval methods to work well. Kind of like Spider, which I think we did in maybe our third episode, I want to say. Yeah.
Yeah.
So it seems to be picking up speed. It still seems to be the case that things are improving, but there's not, like a single pre-training strategy everyone should jump on and let's do it this way.
I mean, that's what makes it exciting.
It's still very exciting and
underexplored area. No, it sounds really nice. I can totally feel how you probably like get this experience in person a little bit better. Like you get a kind of a sense of how what is people excited about more than in online versions. So that's very nice. All right. That said, shall we dive into it as usual?
Yeah, let's jump in.
So let's start a bit with, I wanted to start talking a little bit about kind of a mini history, kind of reflection on the world of neural information retrieval. I remember when I was doing my first course in information retrieval at the UVA at the beginning of 2019, our teacher, Evangelos, actually, I'm guessing you know him. He said that kind of neural information retrieval was still very in its infancy and it was still like very kind of early stages, and how information retrieval was kind of like late to the neural revolution, quote unquote. And I feel like when that changed, it was a little bit with the whole BERT and re-ranker stuff, and when this whole revolution in NLP based on like self-supervised training and BERT and transformers kind of like made it the jump to the neural information retrieval. And I think it's super interesting because I feel like these two things have converged a little, like IR and NLP have kind of converged a little bit in some methods.
The methods, or at least the neural backbones to the methods, look really similar these days, right? So pre-trained language models on both sides, maybe used a bit differently, but the same models are often used. But one interesting thing is that, in NLP, there'll often be a new model that does really well on glue. This is a common benchmark. And so this is the new state of the art. This doesn't seem to be that well correlated with what is the best in IR. So I'm, for example, using Electra, like not old, but, it's after BERT, a couple years old at this point, more than Roberta or something new. Because in IR, this seems to be the right default. In NLP, even though we're still using transformers, the exact transformer doesn't really seem to be the same. So like Roberta was really popular, but I haven't gotten great results with Roberta for IR. It's not bad, but it's just not a clear improvement. So there's little differences like this. But
and if I remember correctly, Electra is the one that proposed to train to do like the pre-training as a discriminator instead of a classification task, right? Like they have like a generator and like a small model that like try to fool the...
Yeah, exactly. So they, rather than doing the masked language modeling, they use the generator to randomly replace some terms, and then they predict whether this was the original term or not. So I guess one advantage is you have a loss on every token now, rather than only the masked tokens or some subset of tokens.
No, that's super fascinating. I remember checking out that paper at iClear, and it was I really loved it.
Yeah. Yeah, but these things have improved IR a lot. So like the transformer models are everywhere. These contextualized embeddings seem really good at content-based similarity.
And like we said, I think in a couple episodes ago, whenever it's not even mentioned, like you normally assume that training on these self-supervised tasks for IR, for instance, starts from a checkpoint of some type of NLP pre-trained. It's like you never start training IR without some kind of NLP base, like some kind of language modeling base or like some kind of...
Yeah, no, that's true. So it's always starting from usually whatever pre-training task was associated with the model, so like BERT, it's mass language modeling, next sentence prediction. And then even like the IR specific pre-training, like I was mentioning at ACL, like we saw with Spider a bit, this is also starting from that checkpoint. So it doesn't seem... I mean, maybe there's no reason to, but people don't go, initialize the model from scratch, train it for the IR pre-training. It's always building on top of, whatever the NLP style setup was, which seems to work.
Okay, yeah, so all of these sort of context to me acts as a justification of why we want to look into NLP paper, because it's a more NLP paper. It's not really IR, information retrieval, which is more of our focus. But I still think it's super interesting to kind of step out a little bit of our comfort zone and discuss this, because there's so many kind of little bits of wisdom that are surprising and fun to discuss. So that said, can you give us, like, as usual, a minute of an introduction of what this paper and logbook does, or like how do you kind of frame this whole thing?
Yeah, well, so OPT stands for Open Pretrained Transformer. And I guess what they want to do is replicate the GPT-3, which is a really common, not common, but really well-known, very large transformer model from OpenAI. So I guess the point of this paper is to understand how well they can replicate it and kind of detail the process. So how hard was it to do? Is it very clean and things just start as you planned at the beginning and go on? And spoiler, they don't. Like, there's a lot of ad hoc changes you have to make as things go, just reducing the learning rate at times and so on manually. Yeah, and I guess another important part of the paper is they want to release the weights, right? So GPT-3, you can use it with an API. I guess you pay for the API, but they won't give you, the model itself. And I guess part of the goal here is to make the model available for researchers who can use it. I guess it's a very large model.
Yeah. No, I think that's super valuable, right, for the research community to sort of learn more about what it takes to train these large language models. That said, I think that we're going to focus most of the discussion on like talking about the logbook and some findings that we have found there, but we should just give like a little bit of a context of what the model is, like the loss functions they're using, a bit like the kind of model sizes they work with. Like Andrew has said, is pretty much implementing GPT-3. So if you are very familiar with that, you kind of mostly know this. But otherwise, what is the what is the architecture they use? What is it based on? And like, it's like encoder, decoder.
Yeah. So what we say for OPT, as you said, goes for GPT-3. So this is a stack of transformer decoders. A decoder is sequence to sequence, meaning the length of the output does not have to be equal to the length of an input. So we've often looked at encoders, which take every input element and you could say rewrites in some way. So it's always end-to-end. Decoders can generate any sequence. They do this by taking some input text as input and then also attending to the previous text they've output. So you can imagine, keyboard autocomplete on a phone, just one term at a time, predicting what the next most likely term is based on what you have so far. This would probably do that much better than what is on the phone, but it wouldn't run there either. So it's a stack of these transformer decoders. And so they train it to do this autoregressive language modeling. Basically, they have some text, and they just try to predict the text. So they start with the first token, try to predict the next token. And then they use something called teacher forcing, I believe. So rather than the model just receiving as input what it has already generated, it receives as input what it should have generated. Right.
Yeah.
So of course it's not going to guess correctly most of the time. So it's kind of given this string, try to complete the next token. Given the new string, try to complete the next token, and so on, just like the keyboard setting.
Yeah, the autoregressive language modeling task.
Exactly. Yeah, autoregressive, I guess, meaning you look at what's been generated before.
Yeah, right. Like it's only like can only attend to previous tokens, but not.
It can't see the future.
Exactly.
Yeah,
exactly.
And then I guess maybe the other missing ingredient is the tokenizer. Is this?
Yeah. So what do they do here?
It's called a byte pair encoding tokenizer. It's not so different than what BERT does. Basically, they create some vocabulary. So here, the vocabulary consists of single bytes, and then they just keep adding to this vocabulary up to some budget, essentially trying to add something at every step that can cover as many possible terms in some vocabulary. So byte sounds a bit different, but ASCII characters like English language, like A through Z, these are all one byte. So this is equivalent to adding in A through Z as like starting tokens, and then also some other bytes. So for example, if you have a more complex character in Unicode, it can be represented using a few bytes. So it's a bit different, I guess, if you move to the multilingual setting, but they focus on English. So I don't think there's a huge difference from like the word piece BERT tokenization for the English purposes.
So this all seems pretty standard. We could quickly say the data they're using, right?
Yeah.
To like a pre-training corpus.
My understanding is it's not totally clear what training data GPT-3 used. This is
It's not completely
so
open source.
I guess part of the goal of this is to see if things work with whatever data they use. So they take the BERT style data, they call it Roberta. So this is like books corpus. This was used with BERT also. And then Creative Commons News, Common Crawl News. I don't think this was used with BERT, but it was with Roberta, I suppose. They also have the Pile, which is a collection of a lot of different texts. So they just take some subsets of this, like Wikipedia. Project Gutenberg is books that are now in public domain. More Common Crawl data.
Yeah, and I guess the only other interesting bit is that they only do filtering of duplicated documents with this min hash LSH algorithm. So basically, like whatever has more than 0.95 checkard similarity in that metric,
right? They filter out.
They filter out.
Yeah,
which doesn't seem to be a very aggressive form of pre-processing, right?
No, I kind of wondered how much of it came from Project Gutenberg. I believe this has a lot of duplicates because it can have like similar editions of a book or something like this. I don't know exactly what's going on, but I've seen this before also. Okay. So when I saw that, I kind of wondered how much of it was specific to Gutenberg. There's probably other duplicates, but it might be that a large part of this is filtering those out.
Certainly, yeah. No, it makes a lot of sense.
And then they also have this Reddit data. The way they use it's kind of interesting, right? Because they need documents. It's not, the model's not trained to look at a conversation, but Reddit is conversation threads. It has a tree structure, so they take kind of the longest path through the tree, turn that into a document, and then keep only that.
Yeah.
So I don't know exactly what effect it has, but it's an interesting.
Yeah, you said before that you would expect it to just end up being like conversation between two people.
I mean, it's whoever had time to talk at each other the longest. That could go poorly or well.
Totally. Okay, that's it. I think we have enough information to jump into the discussion of these logbooks. So for context, if you go to Facebook Research repository, you will find all of this material. What they did is, besides publishing links to download their pre-trained weights and their code, they also have this logbook where they documented, basically the engineers training these and researchers training these kept a log of everything they had to do and of their thoughts and everything, and you can just go through that. Which is a very interesting experiment thing to look into. So we're just going to highlight some things that from that logbook. That said, I think we should start talking a little bit about the preliminary experiments and training run that they do and they document in this logbook. So the first thing so they basically do a lot of experiments with a smaller model of like 1.3 billion. I think it's the one that they do a lot of the sort of preliminary experiments to choose a lot of hyperparameters and things like that. By the way, I forgot to mention this: the sizes of the models that they train.
Right.
They range from 125 million to 175 billion, which is the size of GPT-3.
Right.
So, that's the biggest size, 175 billion parameters. So going back to these preliminary experiments, so they do a lot of these experiments on the 1.3 billion parameter model. And the first thing that surprised me the most was this thing about spikiness. It seems to be like a very salient term that they use. Like they just have these TensorBoard log losses going down, and you see a lot of them are very spiky. Like they have a lot of jumps, and some of them have less of that. And that seems to be like one of the main things they look at to sort of find settings that are stable to train. This is something that doesn't really happen in smaller models. Is that right?
I think
that much.
Not that often. I've observed it occasionally and wondered why, and thought maybe this is some weird part of the training data where it's like nonsense maybe, and the model can't handle it well, right? So if you were to so they're using English language training data. If you were to inject some other language in the middle, I think it would suddenly get really spiky around that point because it's unexpected. Mm-hmm. But commonly with small models, I don't think it comes up as much, or at least alternative is maybe we understand how to train small models well, and things like the default learning rate, the schedule.
Like what people do with smaller models is like they to choose hyperparameters and stuff, they just kind of run it up to a point with different parameters and like just look at how well it performs on a validation set. Whereas here it's more like, let's train it and just look at the plot and kind of interpret it in a kind of this looks very spiky. The loss goes a little bit slower, faster.
That's true. This trying to interpret the spikiness of the loss, I guess, is more in this regime when you have a very large model.
So I find that's very interesting.
Yeah.
I don't know. So about this, I don't know. I have here some thoughts that I had, which is how much of all of these decisions don't look very formulaic, and it seems very much a craft of like people who have done this a lot and have some sort of sense of like, I think this might fix things, I think this won't, but it's not very I don't know, it seems very chaotic. And
I agree. I mean, I think it is a lot built on intuition. And I think because there's not like a comprehensive theory of exactly how all of this works, it's hard to know what to do other than having some intuition and playing around with it, having some idea to change this. Mm-hmm. I mean, there are a lot of explanations for like, I guess, specific phenomena or what single hyperparameters might do, but I don't think there's a way to understand how they all relate to each other. So, maybe, there's some theoretical reason why this nonlinearity is better than that nonlinearity, but how that interacts with everything else, you have to try it, I guess.
Yeah. But what this makes me think of is it makes you realize that even if you have a very good recipe or a pretty good recipe for these, if you try these at home, you're probably gonna fail, I feel like, and you need like a lot of this kind of black magic expertise to make it work in a sense.
I mean, even when we moved from like pre-transformer models to transformer in NLP and IR, the learning rate changed, I think, basically for everyone, right? It went from the magnitude -3 down to like -5. And this was just, one of those black magic things that's handed to you, plug this in. If you don't, it will not necessarily train very well. Just do it this way now that you have a transformer. That's a very good point. I remember when I was studying, I feel like it was pre-transformers, and it was almost like there were memes about how you just probably like use one exponential -3 for Adam, and you'll be fine. Like just whatever. And it's true that that's no longer the case with transformers. Okay, like any other things that sort of stand out to you about the preliminary experiments they do I mean, I thought some of the things they considered but didn't try were interesting. I don't know, like we have them here, like changing the type of nonlinearity from ReLU to GELU, or the other way around, I guess. Changing data, things like that. But I guess these were things that were hard to try. So I guess these were things in Logbook they considered but didn't want to actually do because it would require a full restart.
It would be super expensive.
Yeah, and I mean, who knows if any or which would help and how much? Like, it's very ad hoc. So.
I mean, and when it comes to the training run, without getting into the details of specific issues, because we're going to do that in 10 minutes. One of the things that really found it very interesting and funny was how they really talk about specific nodes. It's like nodes keep failing, right? And they really refer to them as like, node 85 came back. We keep node 7 and 47 removed because they seem to be not doing well. Like, we don't know why, but we just can kind of set that aside. And the realization that once you're working at that scale, it's like, I don't know, it just kind of shifts the kind of class of problems that you're dealing with.
Yeah, I don't know if we said how many nodes there are, but there's like 124 total. So this is interesting. And I think they each have 8-ish GPUs. So I believe it comes out to like 992, if I'm remembering right, GPUs across 124 nodes.
Yeah, no, very good point. So actually, let's jump into this. So like the bit of the more data engineering side of things. You repeat, like it is running on 124 nodes and each one is?
124, each has 8 GPUs, I guess. And so there's a lot of things that can go wrong, right? Any of those GPUs can fail. I don't know if that brings down the whole node or how exactly it's configured. Maybe it does. System memory can have errors in one of those nodes, and now the whole node probably goes down. So who knows what the specific failure reasons are, but I think hardware problems become much more likely at that scale. Yeah. Or GPU driver issues or things like that, right? This is not known for being the most stable driver in the world.
No, totally. That's super interesting. I mean, one of the, I think, running conclusions, or at least for me, is how much babysitting this whole process requires, right? Yeah,
they have someone on call, I guess, constantly for
exactly. They say they have someone constantly on call, and of course this keeps changing because people get burned out, but it's really like their responsibility, and whenever something goes wrong, like to act quickly. Actually they mention in the logbook how in the recipe for like how to deal with things, the price per hour of this whole thing staying idle is $2,500 per hour, so that's pretty important cost. So the babysitting to me, it seems very like huge and important. I think that let's comment on some very also funny thing that I found, which is, I think I know what I mean, which is the temperature issue. Right. They have this place in the logbook I think it's at the beginning, where they kind of describe kind of things that people on call should look for and run. And basically what they describe is to look if whether nodes are functioning properly or GPUs are functioning properly, is to run to check their temperature, basically, which I found super funny because I kind of really expected them to have some sort of monitoring, or I don't know how to call it.
Yeah, system. No, I'm sure they have some logging and production, but I don't know where this is running exactly. I guess they manually have to run the command to check the GPU temperature.
Like the fact that you would look at the temperature of the node too. I don't know, maybe this is actually something super common and I'm just not familiar with that.
Well, so this tool also shows GPU utilization, but looking at the temperature is way smarter because I don't know exactly how utilization is computed, but it's something like a point estimate. So it just depends when you press pressed enter on the command. So it can show something low incorrectly from at least my experience with it. But temperature means that it's recently been used. So and these get very hot. It's a big difference in temperature.
There's some pretty robust physics behind it. Right? If that thing is computing stuff, it gets hot. So like
no, it's a good idea.
So that was super cool.
Yeah.
All right, so let's look into this recipe for when things go bad, right? So like we said, spikiness is a thing that happens a lot. So when they're running this thing, this is like one big training run that they ran through, I think it was like 3 months or something like that.
Yeah, roughly 3 months. I don't know exactly. Yeah.
With their final run, one of the things you observe is that like the model can have, the loss function can have spikes, and then kind of like it all goes wrong. And you have to kind of, one of the main things about babysitting this process is to prevent this from happening or fixing this. So in the logbook, they have this sort of recipe that is like, the loss exploded, like, we don't know why. What should you do when that happens?
Step 1 is don't panic. Step 2 is ping the group chat. And then I guess you have 10 minutes to see if anyone is around to discuss it with. If not, they think you probably should take some action. This is where they say it costs like $2,500 an hour to idle. I guess this means idling all of the nodes. Probably is what it means.
That's what I understand. Because, I mean, the thing is that the thing, like whenever if the loss spikes and you do nothing, like all of the checkpoints that you're saving after that and all of that computation is pretty much useless.
Yeah,
right?
you're going to have to go back.
Exactly. So you're going to have to revert to something previously. So like if you don't do anything, you're losing that much money.
Whereas if a single node goes down, I guess this isn't a huge issue. You have a little less compute, but the rest keeps moving. So,
exactly. Exactly. So what is the next step? Well, what is the next guideline?
So some bias for action. So it's probably better to do something sooner than later due to the cost. And then I guess the next step or suggestion is requeuing. So just starting from the previous checkpoint. We were discussing earlier exactly how this works. I guess it must change the data, right? If they continued from the same checkpoint at the same point in the data, I wouldn't expect anything to go differently. But maybe they're changing the position in the data they requeue from.
Yeah, that would be also my guess. So like the actual wording that they use here is that like they say like requeuing is generally the safest option unless this logbook says otherwise. And then they say restart this job from the last checkpoint and just pray for the best, literally. So I really would like to know actually how often this works, right? Because it's just like reverting the checkpoint and just kind of doing nothing. Like you said, if it's a problem with the data, that there's some like kind of very bad piece of data that makes this whole thing go.
Yeah, but it also should be deterministic. If they're starting from the exact same point in the data with the exact same checkpoint, I think it should be deterministic enough that you run into the exact same problem, right? If you change the data you start from with that checkpoint, you've at least adjusted something about the training. And I mean, if everything is deterministic, I'm just thinking like where changes could come from. Like one is the data, but if the data is the same, maybe do they use like something like dropout or some other like stochastic? If they change the random seed for dropout, that's a good point. I remember them saying, I think they don't use dropout in the embeddings, but they use dropout within the transformer layers. Yeah, so if they're changing this random seed, that.
But I would be kind of surprised if that made.
Yeah, well, I mean, they say also frequently this just kicks the can down the road 2 to 6 more hours, but that can buy you some time to sleep and discuss. So this may be more of a sleep strategy than a fixing the model strategy. I don't
it's
know.
Like, it's definitely better than doing nothing, right? I mean, this requeuing. Like, worst case scenario, the loss explodes again, so you're like back where you were, but not. You're not guaranteed to be losing your compute.
Right, it may work, and you have a plan B in mind, I guess, if it doesn't.
Okay, so when that doesn't work, what are the kind of go-to strategies that they propose?
It seemed like the main go-to is lowering the learning rate. Here they say by some factor like 0.9 times or 0.75 times. They call it the default mode of action. They say this seems to bias a couple days. So I think this seemed to be the most widely used one. They also did some other things, like they say lowering the gradient clipping from 1.0 to 0.3. I think they did this at some point. They might have gone back to 1.0 and then back to 0.3. I don't remember exactly, but there's some playing around with that in the logbook. Then some other things that I guess they didn't try or weren't successful. Clamping of activations, they call it a plan B. So I guess they
they don't reach that.
They don't reach that. And then they tried to switch out the optimizer. So to go from Adam to SGD.
That's one of the most interesting points of discussion, right?
It's a few pages in the logbook. But I at the end of the day, I guess it got back to where they started, right? They ran it.
So can you describe what happened there?
So I don't remember exactly. So I think they did this. They had the spiky loss behavior. They swapped the optimizer out. I think they swapped it out twice. I want to say.
So they were using Adam.
Yeah.
Right?
So they were using the Adam with weight decay, AdamW, I believe. Mm-hmm. And then they tried swapping it out to SGD. I think something about how they swapped it out, they didn't feel like it was going correctly, so they tried to swap out to a different SGD implementation, one they call real SGD and one fake, I think. And then I guess after training this way for a bit, they end up with similar spikiness. So they kind of get back to the same place they started, or at least they feel. I'm not sure exactly how to say whether it's a new problem or a different problem, because it's just it doesn't look right. And at the end of the day, I think then they just go back to the AdamW.
That's my understanding as well. It's kind of it's kind of interesting, right? Like how all these things like this try to move things around, and eventually like you just kind of nudge this kind of loss function a little bit. It's a bit like hitting the TV, you know?
Yeah, no, it's just like hitting energy. The TV. Yeah.
But it works.
Yeah, it's the digital equivalent of hitting a TV. Now there's no like analog electronics to hit. But,
okay, so I think that covers some of the things that we found interesting. Are there other things you want to highlight?
I think not specifically, just the overall amount of like effort and care it takes. It's not just train the model and let it go, right? They have a logbook, 116, 112, something like that pages, with a lot of detail of the babysitting process. So even ignoring like the cost of the compute, you need to have people who know what they're doing, like, watching it near constantly, it seems.
Mm-hmm. No, I mean, and it definitely like speaks to like how, like even if you have even if the GPT-3 paper contains all of the training details, which is kind of debatable as well.
But even if it did,
like replicating that thing is like huge engineering effort. Even if you have all of the kind of pieces and the recipe for it.
Yeah, I mean the guy hitting the TV has changed, right? You don't know if they're even going to make the same ad hoc decisions. It's
exactly, yeah. Anyway, so I think we can just jump into the results. So I guess like my overall sense, like there's not that much super interesting about this, so we'll be quick. My general sense is that they train it pretty successfully, not quite GPT-3 level. Which is what kind of they were going for, but I don't know what surprise or like what would you highlight as interesting bits from the results section?
Yeah, that's my takeaway too. Like I tend to view the results as establishing that they've reproduced GPT-3 in some way. Like the GPT results were look how great this can do at things. Right now, it's more about seeing how well it compares. And like you said, it does seem very slightly worse depending on exactly what you look at. But it's hard to say much about this, right? The data has changed. I don't know if GPT-3 does any sort of output filtering. I guess for most tasks it wouldn't matter. But if you look at like the toxic language stuff, for example, how it does. Yeah, that's the thing. Like
in the paper, they compare it like, it's not so like I think that GPT-3 is like the family of models, and when you use their API for doing inference, they have like specific names for like I think that the Da Vinci is the biggest
175,
one. Yeah, the 175 billion. So they compare it to that, and like you said, that's a black box, right?
Yeah. So, I mean, so they have like this, it's called real toxicity prompts, which is something like you start with a prompt that could go badly and then see if your model completes it in a toxic way.
Yeah.
This model has been trained in Reddit. I think it could do that if it needs to. And it is a bit worse than Palm and then the GPT-3. This is, I think, more clear than some of the other, like they also have zero shot and few shot comparisons where it seems fairly close to GPT-3. In this plot, it seems like GPT-3 is consistently better. But as you were saying, and we were talking about earlier, I don't know what's happening at the API. It's probably in their interest to reduce some of this, the worst output as much as possible.
This is like speculation, but like I would kind of speculate that they probably do some post filtering or some mechanism either in the data kind of training side or at the post filtering side to prevent this.
Yeah, no, that's a good point. Also, we don't know what data GPT-3 used, right? Maybe they tried to aggressively remove, posts that wouldn't be good to train on. Maybe they try to do it all in post filtering. We don't know at all. But here they explicitly say that they don't try to do it, though, right? They talk about downstream applications might need some sort of mitigation for preventing outputs like this, but that's not their goal right now. They don't try to add that.
And interestingly, I believe that if you want to download yourself the bigger pre-trained model, you have to sign some sort of like ethical kind of self. As in, like, it's my own responsibility what I do with this, and I will not use it for nasty stuff because they basically don't provide any guarantee about how this model behaves, and you certainly should not directly apply to some commercial product out there without really thinking carefully about what it will output, because
it's hard to anticipate what it will generate.
Yeah. Okay, and. I think that, they have, like their usual, benchmarks. Like you said, they pretty much established that they replicate GPT-3 pretty successfully. I would like to end this by having like a short discussion or reflecting on, I don't know, this whole replicability of large language models, to what degree it's relevant, how you see as a researcher, kind of how excited are you about these things being open source? Is it really going to make a difference? Not really, because you're not even going to use this anyway, or I don't know. What is your sense of this?
Yeah, it's a good question. I mean, I'm sure, to start with, it makes a difference for someone, right? I'm sure this is now more accessible to people than GPT-3 was, because you can take the weights and load it somewhere. But I think it's still not trivial to use them. I haven't tried. Maybe I'll try with some simple example at some point. But it seems like the weights would be a few hundred gigabytes in that range. So, this isn't going to load into memory on someone's laptop, right? It takes, a real serious machine. Yeah. But I mean, as terms of replication, I thought it was really interesting. I guess what it says is that what's in the GPT-3 paper is more or less enough to replicate GPT-3, right? There's these decisions like what data they used, exactly who was tuning what in what way as things were running. Mm-hmm. They probably matter to some degree, but it is more or less, very similar performance. Mm-hmm. Ignoring the toxicity one, where there's this, it seems like there's a gap. Looking at the standard NLP task stuff, maybe GPT is slightly better, but it's not, a huge difference. It seems, like a very reasonable result. Like 71 versus 69% accuracy, that sort of thing. Mm-hmm.
This is almost like it's almost a philosophical question, but like, what does it mean for a paper to be replicable? Or like, how do you think about what makes a paper replicable? Like, what are good practices? What do you think, especially when you start going into these regimes where like it's like big teams of people like using big compute?
Like,
would you say GPT-3 is replicable, for instance?
Yeah, I would say this has replicated it in some way. Looking at the paper only, would I say it's replicable? I think I would say I don't know, because there's clearly not full detail here, right?
There's the thing. There's some things missing.
It
took a team of very skilled engineers and researchers to pull this off, right?
Yeah. And some of that is probably even just scaling it to train, right? They have almost 1,000 GPUs, and it's model parallel, right? Things are typically data parallel, which is much easier to set up, but it's not going to do the job here. So I guess it highlights that, these issues weren't a huge problem for replicability, but it's very specific to this case, right? Somewhere else you could have data that does matter a lot. And so it's hard to say much until you try it. The question of exactly what's being replicated, I think, is also interesting. So, I mean, the numbers are not the same, right? So 71 versus 69% accuracy, looking at 2 points on one of the plots, for example. But it's close enough. Like the core finding of these models work really well in a zero-shot setting. They perform better in a zero-shot setting as model size increases and so on. I would say that finding has been replicated. Because oftentimes people think about replication as, did I match this metric specifically, right? Is my NDCG still 0.42375 or, whatever? So like the replicability of findings, I think, was the right way to go about it, and I think it's a nice
I guess that's
approach,
a very good point, right? Because I think that a lot of people in who are more computer science oriented, myself included, would think of replicability as sort of kind of running the same, like being able to run the same thing, or like being able to get that same number, not so much as replicating the finding, so to speak, which is more of probably what a lot of other type of research, like in like empirical, I don't know how do you say, like studies, like medical studies, for instance, right?
Right.
Like, replication is about validating whatever hypothesis.
Yeah, or any social science. Yeah, I mean, if you're a psychologist, you can't rerun the same setting twice and ever hope to get the same number, right? We're in a very specific field where we have some hope of repeating something exactly.
Yeah.
But yeah, to me, the replicability is, what did I learn, and does this still hold, right? So something about learning, what do they say? Large language models are good zero-shot learners, something like that with the original GPT-3.
Yeah.
Right, this still holds. You still see the trend. Exact numbers may move very slightly. But
Yeah. No, it's very good point. Yeah. Besides that, we were also highlighting a little bit before we started recording. What are interesting directions where large language models are used in information retrieval or for other tasks, and how these kind of efforts help in that way?
Yeah, so I can think of two not immediate but possible applications maybe. One is just augmenting training data, right? Maybe there's a good way to use this to generate better labels or to generate some intermediate information that's useful. I don't know, but you can generate data using a model like this much better than a smaller model. So maybe this is then useful for training something more manageable. The other thing is I wonder about creating embeddings from it. So it seems like OpenAI explored this a little bit with GPT-3. My sense from reading like Niels Reimer's blog post, for example, is the embeddings weren't working super well.
Yeah, so basically for context, like it was I think 2 months or 3 months ago, right, that they released their embeddings API, which is basically you can get the raw embeddings from GPT-like models and use them for like retrieval or like whatever you want to.
Yeah, you can get the raw embeddings, and then now this is some, you don't have to run the model again. You insert text as input, you've got the raw embeddings, so maybe you can store those embeddings and do something useful.
Yes.
I guess in the case of this blog post, it didn't seem like those embeddings were working so usefully.
Yeah.
But in principle, right, if you had a large language model that could generate them, now you don't need to keep rerunning it.
I'm going to link that blog post from Niels Reimer because I think that was very interesting. And I think that announcement from OpenAI got a bit of a backslash. How I see it a little bit is my sense is that the autoregressive sort of language modeling, which is all the GPT series is based on, does not produce embeddings that are as kind of high quality in a kind of like generalized for any purpose. As well as other like BERT-like span correction approaches. So it does seem like the more you scale it, the better it gets. But I guess that the blog post from Niels kind of highlighted that task specific or like other types of pre-training produce much better quality general purpose embeddings rather than GPT, and that they were kind of a bit overselling it a little bit in their sort of...
Yeah, I mean, in that blog post, according to that evaluation, I think you were better off using a BERT-style type embedding rather than the GPT-3 ones.
Yeah. Definitely check that out if you're interested. I will link that. Yeah.
But it's a hard problem, right? Creating general purpose embeddings is not easy. People often are fine-tuning the smaller models. You can't fine-tune this, I guess. So in that blog post, it wasn't fine-tuned.
Yeah. I mean, it's kind of like almost ill-defined what is general purpose embeddings, what kind of
Yeah.
What is the kind of the set of all tasks of NLP tasks that you want to solve? That's, I don't know.
Yeah, I mean, you can't have a general purpose cosine similarity between embeddings, for example. Like, you very soon have a conflict, antonym and synonym. Now it's right. So at the very least, you need some projection of the embeddings in some other space, or other things have to happen. They can't be totally general purpose with something like cosine similarity.
Yeah. No, but this, like what I think it's a very interesting space. It's definitely not converged, but I do see a trend in this whole space of like machine learning as a service and sort of abstracting away. Like a lot of these transformer models have developed into like models that produce embeddings that are good for a lot of tasks. So a lot of companies are sort of abstracting that away for you and exposing that via an API and charging you for that. And so I think it's a space that will definitely grow in the next year or so. And I mean, if someone wants to grab this OPT thing and host it somewhere and just charge kind of the cost of how much it costs to host, I think that would be great. I'm not aware of anyone who has done that yet, and it's pretty expensive.
No, well. I'm not either. We need some OpenAI competitor to decide. I think I learned a lot from looking through the this paper and on how all of this works, because Yeah, no, it was really interesting to see like the low level details of how hard this is to train, what people have to do on a daily basis, what they think about.
And to me, it's also very interesting how little of that actually translates in the end paper, right? Like the end paper is such a kind of filtered, post-processed story about what happened or like what the findings are, right?
I mean, you can't say, well, we tried this thing and then we thought maybe we should try that other thing and then we tried another thing right in the paper. This doesn't look scientific. Someone asked for an ablation.
All right. Is there any other thing you would like to highlight from this before we close it off?
No, I think it's an interesting paper. I'm quite curious to see how people use it. Maybe it will enable new research rather than using the GPT-3 APIs. I'm very serious to see it. Curious if this becomes more common.
I mean, we're also looking closely at the big science workshop that Hugging Face is spearheading, which they're also basically training a model similar to these in an open source way and documenting their findings. And they already have published some work on the preliminary findings on that. They haven't finished their full training run yet, but I'm also really looking forward to what they find there and what people can learn from it and how they share it. Also, what kind of things they,
and this is a multilingual model, which will be an interesting comparison point because this is English only 175B. I think there's maybe slightly smaller but multilingual, so it'll be interesting to see how it compares for different tasks.
Absolutely, and we will probably talk about that in the future. Okay, so thank you for listening or viewing us, and we'll see you in the next one.
See you.